Here's a question that sounds simple. How do you actually compute square root of 2? And the surprising answer is there is no formula, no neat sequence of operations hands you the exact value. But there is a method so simple a child could do it, and so powerful that it never fails. So let's build it. Welcome to the Numerical Methods, Episode 1. The Bisection Method. Find any root, guaranteed. So, question is, why do we even need a method like this? Some equations are easy. X square minus 4 is equal to 0. You just solve it as x is plus minus 2. But now look at these. A cubic, an exponential mixed with a line, cosine of x is equal to x. For these, there is no formula to rearrange. There is simply no closed form solution. So instead we approximate, and of all the ways to do that, bisection is the safest one to start with. The whole method rests on one big idea. A sign change means a root. If f is continuous on an interval a to b and f of a and f of b have opposite signs, then there must be a root somewhere between them. If f of a into f of b is negative, one value is below 0 while the other one is above. Graphically, the curve starts below the axis at a and ends above it at b. To get from below to above, a continuous curve has to cross 0 somewhere, and right there is your root. A sign flip means the curve must cross 0. That guarantee is the engine of everything that follows. So here's the algorithm itself. Cut the interval in half, keep the half that still has the sign change, and repeat. Step 1 is pick a starting interval where the signs differ. In step 2, compute the midpoint C, the average of A and B. Then in step 3, evaluate the function at that point C. Step 4 decides which half keeps the sign change. If f of A and f of C is negative, then the root is in the left half, so B becomes C. Otherwise, it's in the right half and A becomes C. And in step 5, we keep on repeating this until the interval is small enough. If you remember just one line, make it this one. The midpoint is the heart of this method. Let's run the method on a real example. F of x is equal to x cube minus x minus 2 on the interval 1 to 2. First, check the endpoints. F of 1 is minus 2, f of 2 is plus 4. So opposite signs, a root is trapped inside. Here's the graph. You can see it crossing the axis once between 1 and 2. That crossing is what we are looking for. Iteration 1. Our interval is 1 to 2. The midpoint C is the average of A and B, that's 1.5. Mark it on the axis. Now evaluate f there. Cube it, subtract, and we get minus 0.125. It's negative, below the axis. F of C and f of A are both negative, so their product is positive. Same sign. The sign change must be in the other half, C to B, so A moves up to 1.5. Watch the interval shrink. We've already halved our uncertainty. Iteration 2, new midpoint, the average of 1.5 and 2 is 1.75. This time f of C comes out to plus 1.6, positive, above the axis. Now f of A is negative and f of C is positive, so their product is negative. The sign change is on the left. The root is in A to C, so this time B comes down to 1.75. Interval halved again, now just 1.5 to 1.75. You can feel the pattern now, and you can feel how tedious it gets by hand. Let's just tabulate the rest. Here are our columns, the step number, the interval A and B, the midpoint C, and f of C. Our first two iterations go straight in. Iteration 3, midpoint, evaluate, pick the half with the sign change. Iteration 4, same dance, halve, test, and keep the right side. Interval is getting tight now. Iteration 6, and our midpoint is closing in on the true root. After 6 steps, our estimate is about 1.52. and the true root is 1.521, already accurate to 2 decimal places just by halving. Here's the insight worth pausing on. Every single iteration cuts the interval exactly in half. That means after just 10 steps, your search range is about 1 by 1024 of where you started. And after 20 steps, it's roughly 1 in a million. Halving is deceptively powerful. That's why bisection always works. Slowly, maybe, but surely. Let's make that guarantee precise. Bisection comes with something rare, a written guarantee. The distance between the true root and our estimate Cn is at most the starting width divided by 2n. After n steps, the error simply cannot exceed this, ever. Why it is true? You start with a width of b minus a. After n halvings, that width is b minus a over 2n. The midpoint sits in the middle, so it's at most half an interval away from the root, and that's exactly the bound. And the best part, you can predict in advance how many steps you will need. Say you want accuracy of 0.001 on 1 to 2. Set the bound below 0.001, 2n must beat 1000. Take a log, that's about 9.97. So 10 iterations is all it takes. You know before you even start. One practical question remains: when do we actually stop? There are three common ways to decide you are close enough. First, absolute change. Stop when consecutive estimates barely move. Simple. But it misbehaves when C is very large or very small. Second, relative change. The same idea scaled by the size of C. This one works at any scale and is the reliable default. And third, the residual. Stop when f of C is tiny. Intuitive, but it can lie to you. When in doubt, reach for the relative change. Let me show you why that residual test is dangerous. Look at this nearly flat curve. Our estimates lands here, where f of C is tiny. But the real root is way over there. A small f of C value does not mean you are close to the root. On flat curves, the residual test is fooled completely. So trust the interval width, not the height. Time to try one yourself. Exercise 1. Which of these intervals is valid for bisection on x square minus 3? Here are 4 candidates. Pause the video and work out the signs. I'll wait. Do the signs differ at the endpoints? On B, f of 1 is minus 2 and f of 2 is plus 1. They flip, so B works. On D, plus 1 and minus 2, that flips too. D works. A and C keeps the same sign at both ends, so bisection cannot start there. So the valid intervals are B and D. Exercise 2. A little more work. Run 3 iterations of bisection on x square minus 3 over 1 to 2 and estimate the root. Grab some paper and work all 3 rows before I reveal them. Here's the answer key. Same 5 columns as before. Row 1, midpoint is 1.5, f is minus 0.75. Row 2, midpoint 1.75, f turns positive. Row 3, midpoint 1.625, and we are honing in. After 3 steps, you'd estimate about 1.625, closing in on square root of 3, which is 1.7321. And a challenge to finish. Exercise number 3. How many iterations on the interval 0 to 1 guarantee accuracy of 10 raised to power minus 6? Use the error bound from earlier. Pause and give it a shot. Set the bound below 10 raised to power minus 6. The width is 1. So it's 1 by 2n. That means 2n beats a million. Take a log. It's about 19.9. Round up 20 iterations. And that's the bisection method. Thanks for watching. Three things to take with you. Roots come from sign changes. You halve the interval and keep the half that flips. And the error halves every single step. Next episode, fixed point iteration, the simple idea hiding inside many of the methods you already know. If this helped, like and subscribe and drop your exercise answers in the comments. See you in the next one.